Okay, all right. So sorry for being a bit late. So this is Tuesdays. So I have to host the seminar speaker. So a little bit running a little bit late from that. And then have some problem with Zoom, right? So let's thanks for waiting. Thanks for waiting. So before we get started on the generators, right? So it's for the folks who attended the seminar talk today. After we finish with all those different type of machines, we'll be going to storage, and will be sort of more a little bit similar to the topics that was discussed today in the seminar. Okay, so if you went to the seminar, you thought this was interesting, but some of the math seems a little bit complicated, or the model seems a little bit complicated. That will be going into the into a lot more detail once we finish type 4. Basically, this is type 3. Once we finish type 3, we're going to type 4. After type 4, we'll go into storage, and together looking at storage and a little bit of market design and storage. So if you look at today's talk, basically it's saying that if we have if you look at Texas and to some extent California, the system is showing its age, right? Start to showing its age. It's quite old. We're not very good at dealing with the system when there's a lot of uncertainties. So the idea is, if there's storage, does that make the system better? But does that make the system better? So we'll get into that topic. Together with that, we have to look at something like the basic market design or basic resource allocation in the market. And I guess the difference is, if you look at storage in power system, the storage is still quite undeveloped, right? So it's quite open. How do we use storage, and what's the best way to do this? Okay, so the hope is, this first part of the course, or the machines part, this is a very old story. It's a very traditional and well understood theory. Then we'll transition a little bit, into storage, whereas it's much more open and there's not a clear understanding of it. Okay, so there's sort of a phase transition once we finish machines. Okay. So before we start here, any questions on that? Any questions? Any more questions on the Texas situation? Right, it's getting a lot of attention. Any more questions on that? And anybody wants to discuss? Okay, so if not, then let's continue with this course. Right, so last time, basically, we stopped at looking, where we stopped was looking at this crowbar system. Right, this crowbar system is essentially a protection mechanism and for dumping power, right, for a short amount of time. Okay. It's basically saying it's at the rotor side, but it's outside the rotor. And its usefulness is, if there is a fault, then the power goes through this resistors, and hopefully you can clear the fault. Hopefully the fault gets cleared in a sort of short amount of time. And the challenge with the crowbar system, there's many challenges with it, is the values are difficult to design. There's may create backflow from power electronics. So there's a lot of challenges with this crowbar system. And if you look at the class notes, look at the slides, even stability is difficult to analyze when we have this type of system. Okay, so this crowbar was used early on, again, because it's very easy to build. So you just add resistors to the rotor, and that's it. So it's quite easy to build. But the challenge comes from that once you build the system, right? The challenge comes from if you build a system, the difficulty is that the values and everything there are quite hard to set. They're quite hard to set. So that's a challenge with this type of crowbar systems. And so if we want to improve this system, basically, if having the resistance at the rotor side turns out to be hard to work with, can you think of some way that makes this easier to handle? Right. So if the resistance are at the rotor side, it turns out this is just hard to deal with. This is hard to use, it's not efficient, there's not much control on these. So can you think of what's a better place to put all these resistances? So recall during a fault, we have to dump power somewhere. So we need a resistor. We need a resistor somewhere in the system. Can you think of a better place to put the resistor compared to, let's say, let's just say, at the rotor side? Any suggestions? Is there somewhere we can move the storage? Sorry, somewhere we can move the resistance? So the easy thing to do, actually, the easy thing to do here for this resistance is basically you pull them over in between the two converters. This turns out to be the best thing to do. So this is now called a chopper system. And the name chopper comes from that we have a switch. So this is a switch. This is a switch. And this switch, basically what happens for this switch is you can change when this switch is open and closed. And then you can create a path for power to go, let's say during a fault, through this resistor by having the switch between the power electronics. Okay, so instead of having to the left side of the rotor side converter, we just put in the middle. Okay, the switch gets put in the middle. And then power can be dissipated through the switch this way. Right? So that's the idea for having a switch here. So the reason we want to put a switch here is basically you want to dump power through the DC link. Okay? Basically, since the power cannot go through the stator, then you want the power to you want the power to go through the path with the DC link. To go through the DC link. Then if you add a resistor in the middle, this has a nice property of isolating the two sides. And so you can still transform this sort of AC to DC. The rotor side converter still transforms it. And then what you can do is you can design the rotor side converter to handle this current. If it can handle the current, then you can very easily adjust how much of this current gets divided and go into this resistance. And so this R chopper, RCH, is a resistance, and by changing the switching, you can decide how much power gets routed through this resistance. Okay. And so the requirement is that you need the rotor side converter to handle high currents. But if that can be done, this is a more flexible, more controllable way of dumping power. This is more flexible way of dumping power. This is for how you get rid of this excess energy, how you get this energy out. And one reason you want to dump power, this capacitor. So if you look at the system, this capacitor, this has a design limit. So the voltage over this capacitor cannot be very, very high. What you're afraid of when there is a fault, there will be a high voltage on across the capacitor. What you're afraid of is there's a lot of current shooting through, and that basically sets up a high voltage on the capacitor. Right? So then what happens if your capacitor has too much voltage across it? I mean, anybody ever seen a capacitor with too much voltage?
It can break down.
It can break down, right? Basically, if a capacitor breaks down, it's not a capacitor anymore. It just conducts electricity if it breaks down. And these conductors actually are the limiting design factors in this type of power electronic systems. Turns out the equipment or the part of the system that breaks most easily is this sort of capacitors. And the reason is, if you put a lot of voltage on it, this creates stress on the capacitor. It does create stress on the capacitor, or you set up sort of high field strength in the capacitor. And then this can lead to capacitor breakdown. And for all this high power converters, capacitor breakdown is probably the number one issue they have. As once it breaks down, the whole circuit is useless, right? You punch through the capacitor, then you need to fix it. So the idea is to limit the amount of voltage that's what shows up on this capacitor. Right? So we want to limit this a little bit. Okay? So to limit this, so let's see how the chopper resistance, what it does. So basically, what you have is you have this design limit, right? This is the energy over the capacitor. So I sort of want to store here. Right? So the capacitor is there to store some energy to balance the as a DC link, basically, using the DC link. So you want to store some energy. But there is a limit, right? There's sort of a limit on how much energy it can store. Then if the voltage increases, right? So the energy in capacitor is just half CV squared. So it's proportional to the square of the voltage. Then if the voltage goes up because there's a fault on the grid side, then VDC increases, right? So we have a higher VDC than the design limit, VDCO. Then basically this creates this sort of little, extra amount of energy, right? So this extra amount of energy, if you store this energy in the capacitor for too long, it's not good for the capacitor. Okay? And so the chopper circuit is, okay, let's move this energy somewhere else. Let's get rid of this energy. Okay? Then if you look at the chopper system, what it does is basically, let's say you have this switch. Okay? Let's say you have this switch. What the switch does, this has a duty cycle of K. Right? So let's say this thing has a duty cycle of K. Then the voltage, the average voltage across the resistor is basically just VDC times K, right? As the voltage times the duty cycle. Remember, we're switching on this switch. It's on with a fraction of time, with fraction K, right? So if the switch is open, the resistor sees no voltage. If the switch is open, the resistor has no voltage across it. If the switch is closed, then it sees the same voltage that's maintained by the capacitor. Okay? That sees this voltage maintained by the capacitor, right? Then the power consumed, right? The power consumed by this resistor is just V squared over R. This is the standard equation for power consumed by this resistor. You can substitute the VR squared using VR equals to VDC times K, and you basically get this equation. Then we can compute how much energy I want to dissipate, right? So this is the energy So this energy we want to dissipate. We want to burn through this resistor, this EC energy. Now what this allows us to do is basically to solve for K. So there is, the hope is there is some switching frequency and some duty cycle K, such that by switching the switch at this duty cycle, I can dump this excess energy I have through this chopper circuit, through this resistor. Okay, so that's what you want. Right? That's the idea. If you have a lot of energy, you basically want to get rid of it. And then the way to get rid of it is by turning the switch on. So the energy goes through this path. And to figure out exactly the amount of time or the fraction of time we need to switch this on, and you just substitute this into the quadratic equation, and we get this K. Okay, and we get a K like this. Any questions with this? Any questions? Okay, so if you look at this equation, is there a guarantee that K is between 0 and 1? Right, so the important thing with this equation, there's no guarantee that K is between 0 and 1. And so it's important when you do this calculation to check K is actually less than 1. So because if T is too small, right? So look at the dependence, normally the dependence we want is to look at the dependence of T and K. Basically, T gives you the critical clearing time. If T is too small, then K is large. But if K is larger than 1, this is not a sensible equation. This is an equation that makes no sense. Right? The idea is to have a K that is between less than 1. So that sets up the minimum amount of time you need to clear the energy. So if you cannot clear it, you cannot just sort of dump the energy too fast. This is the limitation of this circuit. So your capacitors still cannot break down immediately. It takes a minimum amount of time to get rid of this excess energy we have. And that's sort of the square root of 1/T dependency. Okay, so for this kind of question, it's important to understand sort of T cannot be too small, right? K has to be less than 1. Okay, so often you'll see a question in your homework or in your exam saying, given a chopper system, what is the minimum amount of time the capacitor has to operate above its rated energy storage? And that minimum amount of time comes from this dependence on T. Okay, so T has to be long enough such that K is below 1, basically. Okay, T cannot be too short of a time. Right? And practically these can be difficult because this shows us up as heat, right? So this energy just eventually becomes heat, and often getting rid of this heat is not trivial. And so that limits sort of how, again, that's another limitation of how fast you can dump the energy. Okay? There's sort of heat restriction on this. But chopper is fairly common protection system. Common protection system we have on turbines. And the idea is this gives you quite flexible control by changing the switching time. Right? And the switching time really is something you can do in real time as feedback control. Because that's something that's very standard in practice. As you change the duty cycle. Duty cycle control is very, very standard in practice. So the idea is you change the duty cycle and then change the duty cycle, and then you change how much energy, this sort of energy you have to dissipate. Any questions on this? Okay, so for this week's homework, you'll see some calculation with the chopper system. The crowbar system is hard to do calculation there because you have to go through the converter, which is quite difficult to analyze what exactly is happening, right? So the crowbar basically is outside the converter, so it's quite difficult to analyze this. Whereas the chopper is a bit easier because you're basically limited by the capacitor. And then the capacitor rating shows up directly in this equation. So it's an easier calculation, easier formula to use. Okay. So this is dumping power on the rotor side, right? This is if there's a fall, let's dump power on the rotor side. You can also do this. You can also do this kind of protection on the stator side. Okay? You can also do this on the stator side. So again, during a fault, as all this is basically, energy has to go somewhere. For wind turbines, you're afraid that there's too much input power, not enough outgoing power. And you cannot, just speed up the blade in some sense. You cannot just arbitrarily speed that up. Okay, so the idea is you can combine what we use in the type 1, in the type 1 turbine, as to still have a stator side dynamic resistance. Okay. So this is the same as before. This is saying if I want, I can have a stator side resistance. So you can basically dump power in both paths. Okay. You can dump power through the stator, or you can dump power through the rotor. You can sort of do it in both ways. And the equations here are exactly the same as we have for type 1. So it's not different. Basically, you have a dynamic resistance, you're changing the triggering angles, and through changing the triggering angles, you can get rid of the amount of power you need to maintain stability for this kind of system. And all of these, again, I think the important thing to remember for all this protection is this is all imagined to operate for a short amount of time, so 2 seconds or so. Okay. All of this is not imagined to last all that long. Right? These are designed to say if there's a fault, let's ride through this fault for 2 seconds or so. After riding through this fault for 2 seconds, then let's, hopefully the fault will be cleared and everything can go back to normal. Okay, these are not designed. These are not designed to operate for a very long time. So these are not actually storage systems. Okay, they're very short-term ways to basically change the dynamic response of turbines. Today, what was talked about more is engineering storage and turbine together. And that's much more explicit engineering a battery or a flywheel or something that together with a turbine. This is not. This is short-term protection. And the idea is, you figure out this is the energy I need to get rid of, and then from that you can compute this as the actual resistance I need. Right? This is sort of the triggering angle I need to have in my protection system. Any questions with type 3 or protection in type 3? Okay, so type 3, the questions for type 3, right, that might show up in the final exam is basically very similar to the ones in the homework. Right? So they're long. There's a lot of equations that are long, but they're not that hard to use. Right? Just know the equivalent circuit and use the equations I show. Okay, so all right, so this is type 3. So next, let's look at type 4. Okay, so this is not much more we can say about type 3. You see type 4 is actually very short story. Okay, so let's look at type 4. Right, synchronous generator. Okay, let's look at what happens when we have a synchronous generator. So synchronous generator, we have all seen before. We have all seen synchronous generator. We have a good idea of how they work. The question is then, why synchronous generator? Right? What's wrong with type 3? Seems type 3 is fairly robust. Right? There's ways to control for reactive power. Right? So it doesn't, the problem with type 2 is you can't control reactive power. You just have to consume reactive power. With type 3, you definitely can produce reactive power by injecting the voltage. Right? Then why did we move to type 4? The type 4 is just synchronous generator. So can you think of some drawbacks with type 3? And that cannot be addressed just by having a induction generator? Are there fundamental limitations to induction generators? Right, so what's a fundamental limitation of an induction machine compared to a synchronous? Yeah. Sorry, go ahead.
It needs a gearbox.
It needs a gearbox. So why does it need a gearbox? Right. So why does induction machine need a gearbox? Right. The reason it needs gearbox is it needs a synchronous speed. Induction generator does not work if there's no synchronous speed. Whatever type it is, it still needs some synchronous speed. And if it has a synchronous speed, it needs a gearbox. Right? It needs a gearbox. You always have to have a gearbox to achieve, not the slip cannot be too far away from the synchronous speed. You need some slip. Right? So this needs a synchronous speed. Right? So it needs actually a synchronous speed from the grid. Right? So one drawback is a gearbox is expensive, it's heavy, it's hard to maintain. Right? And then the gearbox is basically trying to make sure the machine speed is not too far from the synchronous speed. But the synchronous speed cannot be something that the induction generator itself provide. You need this to come from somewhere, right? You need this to come from the grid. So the grid has to provide this. But then let's create an issue because then you cannot use it in a standalone system. Okay? So let's say you have a microgrid. You cannot have a type 3. It's pretty hard to have a type 3 wind turbine powering a microgrid. It's the only generator. Right? It's the only generator because load, for example, has trouble setting the synchronous speed. So the induction generators, even type 3, it's just not still requires a lot from outside. Right? Needs an outside reference. Whereas synchronous generators do not need an outside reference. Okay? Itself can maintain 60 Hertz, right? Being a synchronous generator. It does not need somebody else to tell it what the synchronous speed is. Okay. Whereas synchronous generator, this can maintain frequency. It's very robust. It's quite robust to sort of being the only generator in the system. That this can work if it's only generator in the system. This has no gearbox. Right? Because what happens for this is gearbox is replaced by AC, DC, coupling, DC, AC. Okay, so it's replaced by this type of power electronics. Then reactive power is easy. This can have reactive power. Because the DC to AC converter can simply maintain a phase. It can just maintain can basically achieve whatever phase offset you want with respect to the voltage and current. So then this basically allows you to produce reactive power. This can produce reactive power. because as a source, you can have a different voltage and angle. You control the voltage and angle of your source. Okay? So this can have reactive power. And another good thing about synchronous generator is we're very familiar with synchronous generator. This is okay. We're quite familiar with how the generators work, with how the machines work. Okay, so if you look at type 4, most of the work goes into the sort of AC, DC, DC, AC link. That's where a lot of work occurs. On the generator itself, it's not very hard to construct. So there is a gearbox, so you still need some gearbox, but it's a lot less complicated than say a type 3. The maintenance is easier because most of power goes through a solid state device. So you don't need to, so the maintenance is either works or doesn't work. It's not like a gearbox where you have to maintain the gearbox. Okay, so this is solid state device, and the solid state device gives you together with the fact that it is a synchronous generator, gives you quite a bit of control. Okay, so that's why nowadays, if you look at the very big turbines, are all type 4. Most are type 4. Any questions here about why we're going from type 3 to type 4? Okay, so all the big ones are type 4. So let's look at what happens to type 4. All right, so a synchronous machine, this has a very quick overview, of what we have. Right? But basically, we have a rotating frame of reference and the angle difference there, set up a field, and the field generates power. We have current coming out of the field, and that generates power. So the circuit diagram, we're going to think of the circuit diagram as something like this. Okay, we're going to always think of, right? So the way the circuit works is you have a field current. This excitation, or a field current. This sets up the voltage. This sets up the voltage on the windings, and then this voltage produces power. Okay, so this is a very simple diagram we have. Okay. So I'm going to assume that you have all seen synchronous generators before. We're not going to go into a lot of how they actually operate. We're going to jump from this kind of diagram to directly an equivalent circuit. Okay. We're going to jump from that diagram to an equivalent circuit. We won't spend all that much time talking about exactly sort of references in the synchronous generator. All right, so the equivalent circuit we're going to start up with. First, let's adopt a simple model of I have a machine. This is a generator. This is my mechanical power input. So this is the power coming from wind. And then I'm connecting this machine directly to a terminal. Okay? Directly connected to a terminal. Okay? So this is let's say VT. This is a single machine to infinite bus. Right? So this is a single machine to the terminal. Then what we have is, if you look at this model in a circuit, then the machine model is basically I have some voltage source. Okay? So this machine, this G, becomes a voltage source, an equivalent field voltage being set up. There's some winding resistance on the machine. There's some winding reactance, maybe plus a line, synchronous reactance. So there's some synchronous reactance to the machine. And then this connects to the terminal voltage, which is the grid. Okay, so you can think of this as a grid. RS, XS. And then let's look at the per phase current IA. And the idea, this is sort of quite easy to write down this voltage, this EF, is VT plus RS times IA plus JXS. times IA. Right. So that's the voltage. That's right. So that relates the terminal voltage to the machine voltage, to the equivalent field voltage we have in the machine. So VT, this is sort of normal. This is the terminal of the machine. Okay, this is the terminal in the of the machine. So in practice, if you measure the voltage at the machine, you're measuring VT. You're measuring the terminal of the machine. RS and XS are internal to the machine. Okay, these are sort of inside the big machine itself. Okay, so we don't really measure the equivalent field voltage in some sense, right? What we measure is the terminal voltage. Okay, and we can compute the equivalent field voltage by this equation. Any questions for the machine model? Right, so this is again a standard model we have. Okay. So if you look at the two components, RS and XS, which one is larger in general? R or X for the machine? XS, right? So the chat is XS, that's correct. XS is in general much larger than RS. For synchronous machines, the winding reactance dominance. Okay, so XS greater RS, and RS is often, if not always, ignored. This is pretty much always ignored. We are going to assume there's a lossless circuit. There's only XS. So then it's pretty easy to extend this circuit, right, to the terminal, then connect to the grid. Okay, so normally you have a machine. You don't directly connect to the grid. It's not like your terminal is right next to the grid connection. You may need a transmission line in between. So then we have this type of generator, terminal, transmission line, then to the grid. Okay, so this is a more common model that we have. So this is a terminal bus. Again, this is terminal bus is actually, you can think of the terminal you see when you look at the machine. Okay, this is a terminal you physically see. Then we have a transmission line, right? So this is the we're going to assume the transmission line is again lossless, right? Just characterized by a line reactance XL. And then this VL, this is, we're going to assume this V output, this is the infinite bus. This is infinite bus. Okay. So anybody remember what infinite bus means? So what does the infinite bus mean? We say infinite bus all the time in power engineering. Anybody remember the definition of infinite bus? So if I tell you a bus is infinite, then what does that mean? Okay, so infinite bus is right. So holds constant voltage, right? So this is constant voltage. This is also constant frequency. So we're going to assume basically infinite bus is a perfect AC voltage source. Is a perfect AC voltage. Okay, that's what this is. It's basically something that is at the rated voltage and at 60 hertz. Okay, so this is our model. Right, so this comes from the fact that any one generator is small compared to the rest of the system. So from a generator's perspective, when it looks into the system looks like an infinite bus. And the assumption is whatever the generator does not impact the voltage or the frequency of the rest of the system. So this is true if you're talking about the big bulk power transmission system. This is less true if you're talking about something like a microgrid. For microgrid, a generator definitely makes a big difference. So the rest of the system doesn't look like infinite bus. Okay, so this is something to keep in mind. Although we use this for modeling all the time, nowadays when you look at things like microgrid, right, when you may only have a few big generators, then from each generator perspective, when you look into the system is not infinite. Or you may have many, many small generators, but then they all sort of are coupled together. Then again, the infinite bus model is not so good. But here, so that's a caveat with this model. But here, let's just go, we're gonna assume this is just infinite bus and it's a perfect voltage. So once you have this kind of model, then the equivalent circuit is quite simple. Okay, the equivalent circuit is quite simple. So this is XS, this is the synchronous reactance of the generator. This is XL, this is the reactance of the transmission line. This voltage is called VT. This is the terminal voltage. This is the terminal voltage. And this is the infinite bus voltage, VO. Right? VO is the infinite bus voltage. Any questions about this model? Okay, so then the one thing to remember is for this generator, for this equivalent circuit, right? For this equivalent circuit, often the easy thing is to think of as I have some EF. Some EF. And then I'm looking at some reactance, right? Let's say X equivalent reactance, XS plus XL. Then I'm looking at this VO. Okay. Right, so then if you look at how the circuit works by going from right to left. Okay, so the way you solve the circuit is going from right to left because VO is fixed. Right? So the right-hand side, this output voltage, this is fixed. We have no impact on this. Then basically, EF is a function of, so this is IF, let's say, IF. This EF is function of the current. And then IF, this complex current, is the dependent variable. So basically, the way this circuit works is, given the output voltage and the power you want to deliver, you can solve for the current. Right? We know what the current is. And when we solve for the current, when we solve the current, we can solve them for the equivalent field voltage EF, right? By going through this circuit. Okay. So often the question is find the current, then find the terminal voltage, and then after the terminal voltage, now let's find the equivalent field voltage. Okay. So there's a 3 voltage in this system. The output voltage, that's the infinite bus. The terminal voltage, that's the infinite bus after the line reactance. Then the equivalent field voltage, that's the voltage after the synchronous reactance. Any questions for this part, for this circuit? Okay, all right, so let's take a break now, then we'll do the power calculation. Okay, we'll remind ourselves of the active power and reactive power calculations for the synchronous generator. Okay, so let's break until 1:31. Then when we come back, we'll quickly review the power active P and Q calculation. Okay, all right, let's get started again. Okay, so this is our equivalent circuit, right? And this is a pretty simple equivalent circuit. So finding the active and reactive power of this is also fairly straightforward. Right? So it's not very difficult to find the powers from this circuit. Right? So let's do that calculation. Right? So let's remind ourselves a little bit. How do we find the active and reactive powers of this circuit? So you want to find the power to the infinite bus. Then what we have is as output power, this is the voltage times the current, star. Then it turns out this, right? So if you look at the current, this current is being starred. Right? So it's a bit easier, turns out, to look at the complex conjugate of power. Okay, so this is P minus JQ. So this calculation is slightly easier because to avoid, conjugating everything in terms of current. The reason this is easier is because we always take VO to be angle 0 degrees. This is almost always the infinite bus is a reference bus. So this complex conjugate on the output voltage, this doesn't do anything. This doesn't do anything. This is just the output voltage. So that conjugate goes away. Then the current, if you look at this, right, this current, you look at this current is simply EF subtract V0. Okay, so this is EF, this is a complex number. So EF potentially is complex minus V0 JX. Right? So this is our equation for the complex conjugate of the complex power, the conjugate of complex power. So we can do this calculation. This is V0 expanding EF. Okay, so this is EF cosine delta. So EF, this is EF angle delta. Plus JEF times sine delta minus V0 over JX. This is the equation. Then you can easily separate out this into two parts. One is EF V0 over X, sine of the angle. One is minus G V0 EF cosine delta minus V0. So our P is the real part, and our Q is, right? So remember, this is P minus JQ, right? Because we took the complex conjugate. So if you want Q, you simply put a minus sign in front of this term. So the minus signs cancel. This is EF cosine delta minus V there. So this is pretty easy. Any questions about this calculation? So this is a standard calculation in synchronous machines, right, of the how the active power and reactive power transfer. So this is repeated for the three-phase system. This is repeated for the three-phase system. Right. So if you plot, right, so here basically is we have two variables that we can control. Okay, we can control EF and delta. These are in some sense the degrees of freedoms we have. And then what we want to achieve is P and Q, right? Or you can think of the customer demands some P and Q, and then that will lead to some V and the delta values. Okay, so P and Q gives us V and delta values, right? So there's two degrees of freedom we can control. So this gives us, the ability to control P and Q. Right? So 2 degrees of freedoms, we can control two different quantities. Compared to, let's say, a type 2 turbine, whereas the angle is not a control you have. So remember type 2, the reason, or type 1, 2, and 3, the reason you cannot do reactive power is you don't have control over angle. The developed resistance, right, is a resistance. Whereas here you get to control both voltage and angle, so 2 degrees of freedom. Then if the active power looks like this, we can easily draw what the curve looks like, right? So this is just a sine curve. This is 90 degrees, delta. And then I have a maximum. So for the three-phase system P max, this is 3EF VO over X. It's basically the maximum that we have that we can transfer from the system, right? This is the maximum we can transfer from the machine to the grid. And this is not infinity because we're limited by the voltage magnitude, and we're limited by the reactance of X, the equivalent reactance. Okay, we're limited by this equivalent reactance of X. Any questions here? Okay. So this obviously introduces stability questions, right? So anytime you see a curve like this, it becomes a stability question, because if you see a curve, the question is, which part of the curve do we want to operate on, right? So let's say your customer demand something like, P max over 2. Let's say it wants this much active power. Then you always have 2 operating delta, right? If there's 2 solutions to this equation, because there are 2 solutions for delta. Okay. And the question becomes, which side of this curve do you want to be on? Okay. Which side do you want to be on? So we'll do that. So the rest of today's class, we'll be looking at the stability question. It's quite straightforward, but we'll look at, we're basically, you always want to operate on the right-hand side of this curve. On the left-hand side, sorry, to the left of the 90 degrees. So you want the angle to be small for this type of system, right? You want to operate at smaller angles. Okay? So a lot of that is, if you really want to study synchronous generators, what we covered is a very basic model. Okay, any machines class in power engineering, right? Any machines class will cover things in a lot more detail. So this is, so these are included in the slide. So if you want, you can go read through the DQ0 transformation, so to really understand what's going on in those kind of machines. We'll go through a lot of detail to understand, different couplings and different machines and all the different characteristics. We'll skip this. Okay, we'll skip this time, right? So again, since we want to get to things like renewable integration, we'll simply skip this more detailed machines model, right? But this is included in the slides if you want to read about it. It's not terribly difficult, basically a change of coordinates, but it's a little bit tedious to go through the change of coordinates. Okay, so we'll stay with our very simple model. It just has a sign, just have an angle in it, just have an angle. Okay. All right, so let's switch topics. Let's not switch topic, let's switch slides. So let's look at the stability. Okay, so I apologize, I forgot to post this online ahead of time. So I'll post this after class. Okay, so these slides are not online yet. I'll post them after today's class. Okay. So stability is important because, right? So since most times power system is actually often limited by stability concerns. Right? Since things are dynamic, it's almost never as simple as supply equals demand and you're done. Almost always there's a dynamical equation that's evolving with respect to time. Okay, so that's why stability is important. It's important, right? And stability is important because fundamentally what happens is power demand is set by your customers. Right, as a generator or as a grid operator, you have no control or almost no control in the power they set. Okay, so this then it's up to the generator needs to adjust to meet the demand. The generator needs to adjust to meet the demand. Okay, so it's not we're never considering a single instance in time in actual system operations. As the customer has some demand, then the customer's demand changes all the time, right? Changes second to second. Then the generator has to adjust to meet this demand. So dynamics comes from the fact that the generator has to move. The power output has to move continuously to track the demand. Okay, so we never sort of operating just at one set point and never moving again. Right? That's not the idea. Okay. So this is again a little bit of a traditional viewpoint that only the generator moves and the demand is completely exogenous. You're always treating demand as something completely exogenous to the system. As a requirement that you have, as a constraint that you have to meet. And so nowadays with demand response and things like that, the demand is a lot more flexible. But for now, let's just take demand to be fixed or given, by the customers. And I think of how a generator adjusts, right? Let's say how a generator adjusts. So the way the generator adjusts, the way the generator moves is basically the rotating mass stores, or you can think of this stores energy. This rotating mass stores energy. So this is positive or negative. Okay, this is positive or negative. So this is there's some kinetic energy that needs to be stored. And this is a changing speed, right? This causes a changing speed. Okay, so and the changing speed, basically, if you look at the changing speed, what happens is this speed has to stabilize. Okay, a changing speed has to stabilize. The reason a changing speed has to stabilize is, let's look at the following system, right? So let's again look at this infinite bus. So let's have a generator. This is my output, this is my infinite bus. Then this has fixed frequency. This has fixed frequency. Okay. And if the frequency is unequal, right? So if this frequency is different in steady state, or the frequency actually cannot. And so the frequency of this generator cannot be different than the grid frequency in steady state. Because what happens is frequency is basically a derivative of the angle, right? The derivative of the angle. Power flow is driven by the angle. So if you have a frequency offset in steady state, that means your angle is always changing. Right? Your angle is always changing if you have a frequency offset. Then this changing angle very quickly destroys your machine. Okay, so at steady state, if the grid is 60 Hertz, you have to be also tracking 60 Hertz. So you can have a small deviation to start off with, but then the idea is your deviation should go to 0. This deviation in frequency should go to 0. Right? Otherwise, if you have a steady state error, then things blow up because you have an angle that's just rotating, so the angle is rotating from 0 to 2 pi, and that blows up your system. Okay, so fundamentally in power system, that's why frequency is such an important notion, is that you must track a reference. If you're different in the reference, that means you have a constant acceleration or constant change in the angle. Right? You have a constant change in the angle. A constant change in angle means a constant change in power flow. That means your system is essentially, blowing up around you. Right? So it's a very unstable system. Okay, so the idea is to have recover the frequency. Right? You want to track the frequency. Any questions about this? Okay, so let's see how this is done in the synchronous generator. So in synchronous generator, this is very easy. This turns out to be a much easier calculation than the induction generator, because we have full control of the angle. Right? So the angle is of our control. Okay. So if you look at synchronous generator, what happens is you have some mechanical power into the generator. You're delivering some power to the grid. Right? Let's say you're delivering this much power to the grid. If their integral is not equal, right? If the integral is not equal, then this sets up a difference in kinetic energy. Right? There's a difference in energy. Energy is conserved, so this energy must go somewhere. Right? The energy must go somewhere. So this energy adds up as into the rotating mass. Like J omega squared is basically my mass rotating and storing this energy. Right? I have this shaft and rotor and all these things rotating, storing this energy. Okay. So an imbalance, a non-zero kinetic energy means my angle omega is accelerating or decelerating. My main frequency is positive or negative, so my angle is getting, basically my angle is changing, right? So that means a changing angle. Okay? That means a changing angle, right? Okay, so this is the kinetic energy has to go somewhere, then it goes to the rotor. Okay, and the way rotor works is you have a J omega squared. Okay, J is constant. J is how big your rotor is, as a physical inertia you have in the system. So then omega is a part that changes when Ke changes. So then if you look at the system, then it's quite easy, right? So the time derivative of the angle is the changing frequency, right? And this is the difference between omega and the synchronous frequency, let's say 60 hertz. So if delta Ke is larger than 0, that means your delta omega is larger than 0. Ke is half J omega squared. If Ke is less than 0, this means delta omega is less than 0. So this is the change. This is how the frequency changes when the power is imbalanced. So basically the consequence, right? So the easy consequence is if you look at this model again, this is EF, okay? But what happens is if delta omega is non-zero for a long time, right? Then this angle, right? This angle change. This angle, let's say, changes, right? This angle keeps on changing. That means the current is I changes, then power output will change. Okay? The power output changes. And if this is not stable, so then this may trip the generator, basically. Okay? This may trip the generator. Okay? So this whole thing is a question of whether you have negative feedback or positive feedback in your system. What you want is a negative feedback system where a changing angle makes that the power output, the changing angle and power output is in the direction such that the power, when the angle gets larger, right, means that you have more power than the grid demands. You want the generator to back off to produce less power, okay, to produce less power, right? So you want this sort of negative feedback. Okay? So if you look at the operating characteristics, basically one part of the curve is negative feedback, one part of the curve is positive feedback. Okay? So it's good, right? So together, again, let's write down the equation we have again. Okay? So this is just showing us a little bit of the sort of fuller picture of the type 4 wind turbine. Right? So before we're looking at a generator directly to the infinite bus. So in practice, it's slightly more complicated, not that much more. So basically what happens is you have a terminal. This terminal goes through a full converter, right? This is an AC-AC full converter. We have output voltage. This goes to a transformer, then connect to the farm collection point, then connect transmission line, then connect to the infinite bus. Okay, right? So this is our picture. So we can just summarize everything here. So this picture is not any harder to evaluate. But being more technically more correct is let's look at the voltage after the transformer. Okay, so this is our VL prime after the transformer. Then we can have X. We can include X line and the synchronous reactance in the transformer. Right, so into entire X. So then our model is still quite simple. It's still quite simple. We have VL prime, angle delta. This is X, and this is VG. Okay, we're going to think of VG as the, where our VG is the power, as a voltage as the infinite bus, as a voltage as the grid. Okay. So here we have P out, Q out. Here we have PG and QG, okay, for the amount of power delivered. So we have seen this, right? We have seen this. So this is the same equation from before, just being slightly more technically rigorous. We have VL, which is coming out a transformer. This VL comes out the transformer. Okay. So VL prime is the voltage after the transformer, and everything else stays the same. VL prime times VG over X times sine delta. Right, so we have the same picture again. Right, so we have what we have as PG as V out prime VG over X sine delta. So the max is V out prime VG X. Right, so this is our picture. Right, so again, we have a finite. We have a finite maximum power. It is not infinite. And if I want to make this finite increase the maximum power I can deliver, which variable do I change? Right, so the maximum power depends on the output voltage, the grid voltage, and the reactance. Which of these can I change? Right, so I have three numbers here. Right? So which of these is the easiest to change? Right, so obviously VG you cannot touch. Right? So VG you don't touch. The grid voltage is whatever set by the grid. So we don't touch that. X can be changed. You can potentially change the reactance of the line, although that's difficult. Okay, that's not trivial. Okay. So the thing you change, especially in this type 4 turbines, is increasing V out prime. This is the easy thing to change. Right? This is easy to change is because you're sitting behind this converter. You're sitting behind this converter. So the converter can boost the voltage if you want. Okay, so if you figure out you're getting a lot of power, you want to increase the maximum power, the nice thing of having this converter is you can boost the voltage through the converter. Okay. So the quantity, the control knob, you have to change the maximum power. Most likely in practice is this output voltage, V out of the converter. All right, so that gives us the flexibility. VG and X are hard to change. VG is set basically as some rated number, where X depends on the line. So the idea is just always change V out if you need to change the output voltage. All right, so let's do a calculation, putting all those equations together. Let's do a calculation. Okay. So this is a typical calculation for type 4 wind turbines. So the question will give us the synchronous generator type 4, the reactance of the transmission line, the reactance of the transformer, right, of the full converter, the voltage of the grid, and the voltage of the full converter. So then this says, part A says if the mechanical power is 1 per unit, some nominal value, what is the angle? What is the maximum power you can achieve? If the wind speed is increased, what do you do? Okay. What do you do? Then we can how do we change the voltage? How do we change the maximum voltage? And how do we change the voltage when we have a fixed power angle? So this is really saying, how do we change the control knob that we have, which is output voltage? Okay. So let's compute part A, right? So let's draw the diagram and compute compute each of these parts. So if you look at the solution, this diagram is we have a generator, right? We have a converter. We have some transformer in between. We have a line, then we have the grid. So VG, this is V out. This is 0.2 per unit. This is 0.3 per unit. Right, so under this situation, right, if you look at this situation, then the calculation is quite simple because you can summarize this into a single, right? So we can reduce this to a pretty simple equivalent circuit. This is 0.5 per unit, X. This is VG, this is V out prime. Okay. Right, so for part A, right, part A says PM, the input power is 1 per unit. Right, so this is a balanced power. Power is balanced in this situation. Power is balanced. The voltage is all 1 per unit. So let's compute. What is the angle? Okay, so we have power is 1 per unit. 1 per unit is entering this side. This is 1 per unit going out. The grid is receiving 1 per unit into the grid. Okay, so this is what we have in our system. So then the power we can have, this is fairly simple calculation, Vg x sine delta. Let's call this delta 1. So we have 1 equals to 1 times 1 over 0.5 sine delta 1. We easily get delta 1 as 30 degrees. Okay. We get then delta 1 as 30 degrees. And the key thing to remember is we need to take the smaller angle. right? So there's two solutions to this. There's 30, right? There's 150. Both sine of two angles give you 1/2, right? But here we always, in this type of questions, we'll pick the smaller angle or the angle between 0 and 90 degrees. So you want to be on the left of that curve, right? You want to be on the left of that curve, of left side of this curve, basically. And so this is part A. This is our angle. So the thing to remember for this kind of question is angle is not 0. If power is balanced, the angle is definitely not 0. So a mistake sometimes people tend to make is when they read that, oh, the mechanical power is 1 per unit is being consumed, somehow, people tend to think the angle is 0 in this situation. That's not the case. You need some angle to set up power transfer in this type of problems. Okay, and so you need some non-zero angle to set up power transfer. Okay. So as part B asks for maximum power. Maximum power is quite easy, right? Maximum power is P max. This is VL prime VG over X. So this is 1 times 1 over 0.5, 2 per unit. So this is the maximum power we can deliver. Right? This is maximum power we can deliver. Then part C is quite simple. Part C asks, if I increase the mechanical power to 2.1, can I deliver it? Right? Can I, is it possible to deliver this without changing the voltage? The answer is obviously no, right? This is no. Right? So we have the maximum power we can deliver is 2 per unit. This is less than 2.1 per unit. Right? So we cannot do this. So then the question is, how much of the voltage we have to increase this by? Right? So if we cannot, given this voltage, we cannot deliver the maximum amount of power, or given this voltage, our max power is less than the mechanical power input, then what should the output voltage be? So this is again quite simple, right? The idea is I want the maximum power to be 2.1 per unit, right? I want this to be 2.1. Then I can compute VL prime. This is 1.05 per unit. So I can increase my, now if the power delivered by the turbine is 2.1, in principle, I can just increase my voltage by a little bit, right, to 1.05 per unit to achieve this power. So in practice, that's obviously not a good idea, right? You don't want to just barely meet the mechanical power you can deliver, right? So normally you want some buffer room, right? So that's why we have angle at 60. So part E, we know the delta power angle is fixed at 60 degrees. Then we can resolve the problem of V out prime PG x sine delta. This is VL prime times 1 over 0.5 times sine of 60 degrees equals to 2.1 per unit. You solve this, this is a more robust value of, more stable value of V out. This is about 1.2 per unit. All right, so having a converter is quite flexible for us because having a converter allows us to increase the power. Having a converter allows us to increase the power. And then by increasing this power, we can, but increase the voltage. By increasing the voltage, we can increase the power we can transfer. Okay. So that's the nice thing about having the converter. Any questions about this? Okay, so this is a typical calculation, right? This is so either find the angle or find the maximum power or find the voltage to achieve the maximum power. This is a standard calculation. Right, so let's do one more calculation for this class. Let's do one more. And this has to do with the fact that we can produce both active and reactive power. Okay, right. So as we said, we have two degrees of freedom, voltage and angle. Right. So there's maybe two things we can control, right? Both voltage and angle. So here is the same setup, So everything up to here is the same. The only difference is I want to deliver this much real power and this much reactive power. Active real power to the grid. Okay. So now I'm computing both the voltage and the angle. So this alpha voltage is no longer fixed because I need to achieve both real and reactive power. Okay, I need to achieve both, right? So now we have to find two variables, the alpha voltage and the angle, to make this happen. So let's try to make this happen. All right, so let's do this calculation. It's a little bit, so slightly, difficult, but it's not very difficult, right? So it's not. Okay. So let's solve this question, right? So we have the active power. This is V out prime Vg over x is equal to the active power. We have Vg over x, V out prime cosine delta. Forgot sine delta is Pg. Cosine delta minus Vg. This is Q, right? Amount of reactive power we want to supply. So we can plug in some numbers. Okay, plug in some numbers. We have Vg over 0.5 sine delta. This is equal to 1. We have 1 over 0.5 VL prime cosine delta minus 1. This is equal to 0.5. So we have two equations, two unknowns. But the two unknowns are multiplied together and we have sine and cosine. Okay, so this is the slightly non-trivial part of this, right? So you have enough. So it's not linear, it has a sine and cosine associated with it. Okay. So don't, if you look at this question, don't just directly, use a computer and try to solve this. That's a nonlinear set of nonlinear equations. This type of equation I set up such that it's not that hard to solve. Because you can reduce, clean up the equation a little bit. We can get them to be in this form. This is just cleaning up the equations. We can get them to this form. Now, how do I solve this system of equations? What's a simple trick to do to solve this? Right, so without using computers or anything like that. Okay, so the simple trick here is basically you can just divide them. Okay, we can divide these two equations. This is just tangent delta because VL prime cancels. And this is just tangent of delta. But this is 0.5 over 1.25. Okay, right? So this tangent delta. So you can solve this. So this gives us delta as tangent inverse 5. This is 21.8 degrees. Okay. Then you can plug this in to find VL prime. Okay, so this is, you can plug this back into any of these equations, figure out VL prime. Okay. So this is another typical question you'll see for synchronous generators, right? Solving for both active and reactive power. I think to remember, even though the question is nonlinear, it's still very easy to solve. Because it turns out you have V out multiplied by sine and V out multiplied by cosine, as shows up in this kind of equations. Then just sort of simple division and figuring out what the solution is. Okay. Any questions about this? All right. Okay. So let's stop here today. Let's stop here today. Next class we'll finish type 4. We have maybe 20 minutes to go in type 4. Then we'll go into renewable integration. Okay, we'll go into renewable integration. Okay. So as also a reminder, we have a talk by company Thursday, right? So Thursday the company will do the talk. Then we'll finish type 4. Then we'll go into renewable integration. Right? So there'll be a new homework out this Wednesday. Basically focus on, mostly on type 4 generators, right? All right. Thanks, guys. See you on Thursday.